Here you go.
Okay, thank you, Sala. I will just start my screen sharing. Here we go. Yes, today we will have a look into construction of simple and small RAS as part of the webinar series on aquaponics, aquaculture, and hydroponics of FrontAg Nexus and DOLORES projects. Here. Yes. Yeah, most of you should already know me by now, so I will just introduce our expert that will join me in this webinar today. It's Dr. Olusegun Oyebola from the University of Ibadan, who will share some of his experience with aquaculture and catfish that they have in their Department of Aquaculture and Fisheries Management. We will have about 4 parts in this webinar today. First part will deal with aquaculture systems, different types of aquaculture that exist, and the control strategies that are linked to them. Then we will look into the culture units, where the fish live in an aquaculture system, and afterwards treatment devices that maintain the water quality in the culture units. And as the last part, Dr. Oyebola will just add a few of his expert experience at the university. So let's start with part 1, aquaculture systems, different types and control strategies. In general, we have different types of aquaculture systems where some are linked to the environment directly and some have a controlled link to the environment. The most simple kind of aquaculture in general is fish ponds. Normally they are quite extensive, so not many fish in quite a large volume of water. And the water quality is oftentimes only controlled by the biotope that is inside of the fish pond and at the borders of the pond. So algae, plants, bacteria all live together with the fish in the pond and maintain the water quality that is needed for the fish to have a happy life. Then we have, and obviously this kind of aquaculture is directly linked to the environment. So if we put a lot of fish in a pond and we feed them a lot, we will directly have an impact on the pond and on the environment that makes the pond live. And the same accounts for net cages. They are potentially quite intensive because in this small cage that we see here on the photograph, there could be potentially quite a lot of fish. And in general, the way that they work is that they have a large water body surrounding the cage, like we see also on the photo. The lake where the cage is in is quite large. And this is the way how the water quality inside the net cage is controlled, because everything that's produced like waste from the fishes in the net cage can get out of the net cage and suspend in the large water body of the lake. And there again, the biotope takes care of handling the waste products of the aquaculture. But here also the aquaculture has a direct link to the environment and a direct impact on the biotope and the water quality in the lake. So if we have a lot of net cages or a lot of fish and a lot of feed again, we can have quite a negative impact on the environment. Flow-through systems are a little bit more enclosed. They maintain water quality by a constant flow of makeup water that comes from a freshwater source like a lake or a river, a rivulet, whatever. It needs quite a lot of water because we have a constant flow of water inside of the aquaculture. These can also be quite intensive, but then we would need even more water. And then it depends. If the outflowing water with the waste products from the fish is not treated with some treatment devices, we will also directly have an impact on the environment where the wastewater flows in. So here we can say if we have good treatment afterwards, flow-through system is potentially not very harmful to the environment, but it can be if we don't have enough treatment devices or none at all. And then the last system that we will look into more in detail today is recirculating aquaculture systems. These are generally very intensive, so a lot of fish compared to the other aquaculture systems. And the water quality is controlled through filter systems because most of the water, up to 99% of the flow through the culture unit, will be recycled inside of the system. So we have more or less no direct link to the environment, and the little water that runs through the system and is let out to the environment will be well treated. So the impact to the environment is in general quite low. Recirculating aquaculture systems have been tested with a lot of different species already. So we see that there are, if we just pick some of the well-established fish species for recirculating aquaculture systems, we see cold water fish, warm water fish, omnivores, carnivores. So we can say that almost every kind of fish is potentially fit to be reared in recirculating aquaculture systems, but the system has to be adapted to the fish species so that the water quality for the species is just as good as it needs to be. When we're designing a recirculating aquaculture system, we have to consider some things. Most important, as we already repeated several times in the webinars before, is that the fish create with their metabolism some waste products that go into the water, like solids, like nitrates or ammonia, nitrogen, that have to be filtered out of the system again so that we can recirculate the water and maintain water quality that is within a range that is good for the fish species reared in the system. And we already saw also this graph several times, but I repeat it here again because it's so important. We will, for every water quality parameter, we will have an optimal range where the fish are really well, where they will grow in a manner that is optimal for us. We will have a tolerance range where they don't die, but they don't grow that well because they are already in a zone of physiological stress. And we should try to stay always in the optimal range and really take measures if we get out of it and into the tolerance range, because anyways, we don't want to get out of the tolerance range because then we are risking to lose our fishes. One of the main characteristics of an aquaculture system is the so-called carrying capacity. And this is the maximal biomass that can be supported by the system. And normally this is expressed in kilograms for the total system. And if we consider the production volume of the system, we can break this down into a kilogram per cubic meter value. And this normally corresponds to the maximum fish density that the system will be able to carry. As I already said, the different aquaculture systems that exist correspond to different control strategies for the water quality. In a pond, we have more or less no water exchange. That's not really true because there's rain running in, there's some water that evaporates, or there's some exchange with the environment. But if we are looking at it a little bit more general, there's no real water exchange, and we could expect that the waste products from the fish will accumulate infinitely in the systems, But as we have a biotope linked to the pond that takes care of the waste products, we can control the water quality even without water exchange in a pond. But it has a price, and that's that we have to use it very extensively. Then we have the constant flow through systems, where the water quality is maintained by the amount of water that runs into the system and out again, carrying away the waste products that are produced by the fishes. And if we have more fish, we just need a larger flow. And then there are the recirculating systems that can recirculate up to 99% of the flow through the culture tanks or culture units. And the water is filtered by different filtering devices and can then be fed back to the culture unit. And in between, there are some kind of systems that are a little bit between the constant flow through concept and the recirculating system, because if we recirculate less than 99%, let's say 50% of the flow, we will still need 50% of a flow through that constantly takes care of the water quality. But in general, in recirculating aquaculture systems, we are looking to minimize these flow through amount to as few as possible. So an important thing to know is how much of which waste product is produced per day. And normally this depends on the feeding rate that we have. And if we design the system, we normally design it for the extreme. That means that we are looking how much fish would be the maximum amount of biomass of fish in the system, how much feed would they need, because this would be the maximum of feed that we use in the system. And then we will know how much of a certain waste product will be produced by these maximum amount of fish with a maximum feeding rate per day. And normally this is a rate that is given in grams per day. And if we want to know how much of this product is produced as a mean value over the day, we can just transform the grams per day in milligrams per second. And that's why here I divide the daily rate by 86.4, because this is basically the transformation from grams per day in milligram per second. But then this would not be the production rate of the substance that we look into if we design our system. And that's because fish with their metabolism don't produce a mean over the whole day, but they have like a digestion function that starts with the first feeding of the day and then goes up to a certain maximum and then goes down again to a rate that fish produce when they are not fed. And that is why we don't have to look into the mean production in milligrams per second, but into some value that corresponds to the peak production on a daily basis. And here we have to know that some of the waste products are excreted via the gills with respiration. That's, for example, the ammonia. And others, like the solids, are evacuated with gastric evacuation with the intestines. And if you look at the mean values of the production compared to the peak values on a daily basis, we will have to multiply the ammonia production, for example, as it is a gill ventilation, with 2, the mean value. And for solids, for example, we have to multiply the mean value by 4. And it is very important to respect this when we design the system, but also later when we monitor the system. Because if we are measuring water quality values, it makes no sense to measure them when fish are not producing the waste products and if the system is not at under heavy pressure. So we should also take our water quality parameters when we are near the peak values of the production of the different substances. Meaning normally that's about 5-6 hours into the day after the first feeding. Now, how do we know which flow rate we need in the fish tank? If we have a certain, normally we look, let's put it like that, at the mass balance. So everything that is produced as a waste product into the culture unit has also to go out to be in equilibrium. So if the mass balance is in equilibriums, also called steady state, what goes in, the addition rate of a substance, would have to be equal to the removal rate of the substance. And inside of the culture unit, removal rate corresponds to the concentration of the waste product inside of the tank multiplied with the flow out rate. And the addition rate is what flows in, also with a certain concentration. That might be 0 if water is completely clean, but usually in a recirculating system, we still have a little bit of this product also in the inflow. And what is produced as a peak rate by the fish. And if we say these two terms have to be equal, and we know that what flows in flows also out, so the flow rates from the inflow and from the outflow are also equal, this comes down to this formula that we see under 5, that the flow rate that we need for a certain waste product is the peak production rate in milligrams per second divided by the efficiency of the treatment device for this product. So for example, if we know that our solid separation has an efficiency of removing about 70% of all the solids every time that the water runs through the filter, we would put in here 0.7, and the maximum allowed concentration for our fish species of this waste product. We will look into this again in 2 weeks when we are talking about operation of RAS, and then we will also do a little example of these calculations that makes it probably a little bit clearer. But I wanted to state this already today, that this is one of the main or basic considerations that we have to look into if you want to design a recirculating aquaculture system and the different treatment devices that we would need. So the components of RAS are usually the culture units where the fish live, different treatment devices that build the filter system that are usually made up of a mechanical filtration where the solids are taken out of the water, biological filtration where mainly ammonia is transformed into nitrate and nitrate, and microbial control that will clean the water from viruses, microbes, and very fine solids sometimes. But that is only needed if we exceed a certain intensity or density of fishes in our system. And then we would have something like oxygenation or aeration. Also, this depends on the fish density in our system. If we don't exceed 45 kilograms per cubic meter approximately, we can get away with aeration, so only pumping air into the system with air stones or some other device to transfer air into water. If we exceed this value, we will definitely need oxygenation that usually takes place outside of the fish tank in a separate device just before water is fed into our culture unit. And if you look into system complexity, we can see that with the amount of flow that we want to reuse, and also with the intensity of our fish farm, so more kilograms per cubic meter, the complexity of our system will get more complex with the flow reused or with the intensity. So the first thing that we would need if we get a little bit more intense will always be aeration. Second thing will be solid removal, and then ammonia and carbon dioxide removal. And these are the first three things that we need. Even though we are not reusing really much of the flow, so 50% is not recirculating really in full. But if we get closer to 90 or 99% of the flow reused, then we definitely need alkalinity addition to maintain a constant pH value in the system. We also have to take care of fine solids removal, microbial control, and at the end also nitrate and dissolved organics removal. If we have a system that is not very intensive, so let's say below 45 kilograms per cubic meter or even lower, we can reuse a larger part of the flow, let's say 90 or 99% even, without using all of the above methods. But this is really if we go not going very intensive, and because recirculating aquaculture systems are oftentimes quite an investment, many people want to have a lot of fish inside of the systems, and that's why oftentimes we also see the full band of different treatment devices in these systems. So after having said that about the general system conception, let's have a look into the culture unit. What would be the habitat for our fishes? What is important inside of our culture unit is that we have enough oxygen inside of the culture unit, so that the fish can I don't know the word in English at the moment. Respiration was a word. And this will reduce, in fact, the dissolved oxygen inside of the tank and increase the levels of ammonia and carbon dioxide within the tank. They will excrete dissolved solids. And that's also where we put the feed inside of the system. So it's quite an important part of the system because that's where the fish live. And the main purpose of the whole system is to maintain the water quality inside of this culture unit that fits the need of the fish. Culture units in aquaculture can have very different forms. Oftentimes we see circular tanks. The huge advantage of circular tanks is that they have a very high self-cleaning effect, a very good mixing of the water body, so the consistent water quality in the whole tank. They have an excellent stability, but a little backdraw, they don't use the space that is available for aquaculture very efficiently, because with a round form or shape, there are always angles that are not used. And that's much better in rectangular tanks, but they have the backdraw that they have a quite low self-cleaning ability. They have in the corners or at the borders different water quality than at the middle because the flow is not as consistent as in the round tank. And that's why some people invented a double D-form fish tank that combines a little bit the advantages and the disadvantage of both other forms, because we have a good mixing of the water. It has quite some self-cleaning ability, but it needs more material than the other tanks. That's a little backdraw of this form of fish tank. and a more complex design than the other two. Which materials are oftentimes used in aquaculture? Circular tanks are often made up of PE that has a high UV resistance, low porosity, which is very beneficial because it prevents the attachment of a biofilm, and also thermal stability. Yes, but we have to take a little bit care of statics because the plastic wall is not very thick, and that makes it a little bit unstable. But as long as we stay round, it stabilizes itself. Then we have steel with liner, also quite UV resistant and thermal stable. It's very easy to install. That's why it's oftentimes preferred. But it is a little bit tedious to attach connectors because we see here this structure that the steel has typically makes it difficult to plug in some kind of piping. Then we have the concrete that is also very common, that can be round as well as rectangular, whatever. Backdraw of concrete is that it has a quite high porosity, so we will have quite some biofilm that's created on the walls of the fish tank. And at the beginning, if we put it into operation, we will also have a high alkalinity of the concrete that would have to be considered and observed because this may produce problems with the pH. And yeah, last but not least, tarpaulin is also common material where also quite various shapes are possible, like rectangular, almost round, whatever. One backdraw that I always see is that there's quite a high pressure on the tarpaulin. In practice, it seems to work, but I'm always a little bit afraid when I see the bulging and everything of the tarpaulin. It's easy to install, but sometimes it may be tedious to attach connectors again in a way that no water leakages occur. Another thing that is quite important with the culture unit are the covers, because fish tend to jump and to get out of the culture unit by that way from time to time. So we don't want that to happen. That's why we can put some nets over the fish tanks or mesh covers. That's also a protection from predators, obviously, if we are in the open air. But we should consider that if we use mesh covers, we probably need another protection from sunlight to prevent algae growth inside of our tanks. And another alternative would be a cover that is opaque on itself, like tarpaulin cover again, that we see on the other photograph, that's providing shade at the same time as it protects the fishes from jumping out of the fish tank and also from predators. One small backdraw might be that if we remove the cover, the change in light is quite violent for the fish, and that may scare them, and that we try to prevent usually to scare the fish. So that's a backdraw, and we have to make up a little bit which way to protect our fish would be the best in our case. Then I wanted to show you some aspects of the self-cleaning capability of the round fish tanks, because this is really a huge advantage of round fish tanks. In a round fish tank, we normally have two different flows, a primary flow that is clockwise or counterclockwise. That depends mainly on the direction of the inflow that initiates this flow over time. And this rotational primary flow will help to make particles go down to the bottom of the fish tank, and also to make them arrive at the middle of the fish tank, which is also supported by the secondary flow that we see on the right-hand side. That also helps to transport particles from both sides or all sides of the tank to the middle of the tank. And then we have an easy time of getting the particles out of the fish tank if we use, for example, a bottom drain, or a solid lift overflow would also be fit, that sucks the solids from the middle of the fish tank out of the tank. If we use a bottom drain, we always have to think about a standpipe outside of the fish tank, because with the bottom drain, we are always risking to lose all the water when we have a leakage. So the standpipe outside will make sure that the water cannot go further down than the height of the standpipe, even though we have a bottom drain. Oftentimes, the self-cleaning ability of the fish tank is combined with a dual drain system, meaning that we are sucking only part of the water out at the bottom of the fish tank, and the remaining part with a skimmer on the surface of the fish tank. The big advantage of that is that we only need a small amount of the flow to get all the solids out of the fish tank. And if we only have to clean these smaller flow from the solids afterwards in our solids removal treatment, then we will have an easier time to settle out more of the solids with a smaller flow. That's the main reason why I really like dual drain tanks, because we can reduce the flow that goes through the bottom drain and that transports out the solids. And if you look at the inflow to the fish tank, we also have different strategies there. We can have a simple drop if we have an aerated inflow, or some kind of a spray bar. This one is probably not the best example, because in a round tank, I would put this more where there's the middle of the tank, and then do at the one hand side of the round tank the spray bar in a different direction than at the other half, so that we still add to the circular movement of the water with the inflow. The advantage of both of these inflows is that we have a certain disturbance of the surface tension inside of the fish tank, and that adds to the aeration of the fish tank. And also, if we are looking at the spray bar, this quite large contact surface that these different droplets that run into the fish tank have with air helps to aerate the systems, even if we use also air stones to aerate the system. With very low intensities, this can already be enough to aerate the system. But if we have high fish density systems, we will use oxygen. And then we don't want to get the oxygen-rich inflow water in contact with the air, because then we would lose the saturated oxygen out of the water. That's why in oxygenated inflows, we usually see that they are submerged in the culture tank, so that really all of the oxygen-enriched water gets in the fish tank without getting in contact with the air. Regarding the removal of the flows, I already mentioned that we can use a dual drain tank where we have one outflow at the bottom, either a bottom drain or a solid lift overflow, for example. And the main part of the water will get out with a skimmer that is on the water surface. And in larger systems, the skimmers could be much larger than what we see here. These are quite small skimmers. So don't get confused. In larger systems, we will probably have a much larger skimmer also. And even in quite small systems that use aeration, this aeration can add again to the removal of the solids if we place the aeration at the right spot. If we are looking here, this is a drawing of the SLO that we had here in the first image. I go back again to here. Here, this is a SLO. And in the image that I showed with the aeration is just set up above the SLO inlet. And this helps to create, again, this secondary rotational movement that helps to transport solids at the bottom of the fish tank towards the solid lift overflow. So we have a dual benefit of aeration in the way that it aerates the water and adds oxygen for the fish. And at the same time, it helps to evacuate the solids from the fish tank. Then a very important point in the fish tank design, but also in the design of the aquaculture in general, is the flow velocity inside of our pipes. That is because, especially when we are looking at solids, we want to have a high flow velocity that transports out all the solids out of the fish tank. And with the SLO, like we see here, the solids have to go up first with the water stream. That means that the water stream has to be that fast that the solids won't settle out inside of the pipe. And second reason is that we want to prevent biofilm to build up on the walls of the pipes, because this will lead to clogging or lower flow rates over time. So usually we say that we want to have flow velocities, of 0.7 to 1.0 meters per second, which is quite fast. And oftentimes we don't get that in small RAS systems. So we have to keep that in mind, that our flow velocity might be not fast enough to prevent biofilm growth, and that we have to clean our pipes from time to time in smaller systems, especially. In larger systems, that's not that much of an issue because we have these higher flow velocities. And normally, and that is what is shown in the graphics here, is that if we are looking at a certain flow rate or flow volume that we will have to lead through our fish tank, we can influence the flow velocity by the diameter of the pipes that we use. Meaning larger diameters lead to slower water flows, and smaller diameters lead to higher flow velocities. And we have to find some kind of a sweet spot, because if we go too small, we can again get problems with clogging. So taking the smallest pipe is not always the best choice, also because this adds to the head loss of our system, meaning that we need to invest more energy to transport the water. And this is one of the things we have to figure out, especially in smaller systems, that we find the spot where the flow velocity is as high as possible, but we don't use too much energy to produce this flow. How do we design the flow rates in our fish tank? And here again, I'm talking of small scale and simple RAS, not larger ones, because then we have to calculate it a little bit differently. In a small fish tank, we can usually just look at the flow rate through the SLO that we want at the footprint of our fish tank. Let's say it's 1 meter square. Then 1/10 of this 1 meter square will be the flow rate that we need through the solid lift overflow to get out all the solids of our fish tank. What would be just 6 liters per minute in this case, yeah? Because 1 divided 10 is 0.1 liter per second, and this corresponds to 6 liters per minute. And if you want to know to what if this produces a flow velocity that is high enough to get all the solids out of our system, we can just look at the velocity of the water in our SLO, which we can calculate by dividing the flow rate, let's say 6 liters per minute, by the cross-sectional area of the SLO to have the velocity of the water. And this velocity of the upstream inside of our solid lift overflow has to be larger than the velocity of the particles settling down. And if we calculate the settling velocity of particles, for example, with Stokes' law, that is quite well known and oftentimes used, we can compare these two velocities, and then we will know if the velocity in our solid lift overflow is high enough to transport out, for example, particles up to a diameter of 10 millimeters of our fish tank. Okay, that was the part about the culture units. Then let's have a quick look into the treatment devices. Usually, the whole system will be made up of our culture unit tanks, and then we will have a solid removal, a biological filtration, and then, depending on the intensity of our RAS, disinfection, degassing, and oxygenation of our water, and an additional sludge treatments for the solids or the sludge that is collected into the solid removal. And this order is quite important because the first thing that we always want to do is to remove solids, because solids have a negative impact on biological filtration and also all the other steps that we see here, one after the other. Second step will be, in general, biological filtration, so transforming ammonia into nitrate and nitrate. Then we will have a disinfection unit if we have it. And before we oxygenate the water, we will have the degassing unit, because we want to get the total gas pressure as much down as we can before we add the oxygen, so that the saturation with oxygen will be as optimal as it can be. For every one of these treatment devices, we will have to ask us the same questions. Is the treatment in our aquaculture system needed? Because not every treatment is always needed, as they depend, for example, on the intensity of our RAS. How high is the contamination of the process water with a certain substance? Do I really have to take care of it with a dedicated treatment device? Then the question, what would be the appropriate device in my system? Because for every treatment step, there are usually different devices that are available, and we should pick the one that offers us the best value for the investment with respect to the aquaculture system that we are planning. And we also have to take into account that some of the devices that are available probably fulfill more than one function in the system. So, for instance, some might serve as a biological filter and at the same time serve as a degassing unit. And then we have to ask us the question, are there waste flows that are produced by the treatment device that we have to take care of, or can we use them again in a larger system as a secondary resource? Like, for instance, the nutrient-rich water or the sludge of the solid removal process that we can somehow reuse in our hydroponics part of an aquaponics system. So first step, as I said, would be solid removal. Most of the conventional clarifiers don't remove fine solids, but that's not really a problem if we take care of them in later steps. But as we filter out organic solids, the sludge that is produced can produce anaerobic conditions, exert a certain oxygen demand on the system, support microbes, leach nutrients. So we should get rid of the sludge as fast as possible again to maintain water quality inside of our system. Very common solid removal devices are sedimentation devices, like, for example, radial upflow filters or just simple sedimentation basins that can filter out coarse particles of the system. We have filtration systems like, for example, rapid sand filters that can filter out finer particles. And if we are going a little bit more high-tech, we can also have kind of one-stop solutions in our system, like screen filters or drum filter here in this photograph, that filter out most of the sediments in one step. So coarse sediments and the finer sediments in one step. But this comes with a higher investment cost and also more energy use for the system. So that's why I decided in the course of this webinar to look more into the sedimentation and filtration devices, because I think they are, if you don't exceed certain fish densities, quite useful and not very expensive. And if you look at the coarse solid removal process in a radial upflow filter, this is shown here with two different designs. One is based on just a blue barrel, which would be fine for very small systems. And the other one is made of PE and useful if you have a larger system. But the function is always the same. We lead in water here in the middle of the radial upflow filter. With a deflector pipe, we push it down into the filter, where it again changes direction and floats up to an overflow. That is the final destination of the water in our filter, where the water can run out of the filter again. And the idea is that we slow down the velocity of our water flow so much that as many particles can settle down in the filter as possible. And that is done with an increase in cross-sectional area of our tank. Yeah, we see here our inflow is quite narrow. That is by purpose, because we want to transport out particles that are as large as possible. And then we have already a larger pipe here that leads the water down, and then really large extension of the cross-sectional area when the water gets up again. And this helps us to settle out as many solids as possible that will collect here at the bottom and can suck out of the device on a daily or by daily basis to get out of the system completely. Here again, the calculations are a little bit the same as I already explained for the pipes, because we also divide the flow that goes inside of the filter. with a cross-sectional area. And this helps us to calculate how small the particles may be that we settle out in this filter. And we can also go the other way around, define which size of particles we want to settle out, calculate the settling velocity for these particles, and then calculate how large the cross-sectional area of our filter should be. And then we come up to a certain value, let's say 100 micromillimeters, that will settle down in the radial upflow filter, and everything that is smaller will obviously go up with the stream to the overflow and get out of the filter without being filtered. And all these particles will then go to our fine solids filter that might, for example, be a rapid sand filter that exists in two different versions. One is the upflow rapid sand filter, one is the downflow filter. Basically, they are more or less the same. The difference is that the upflow filter is probably a little bit more efficient because water goes up and the solids don't gather on the surface of the filter, but inside of the filter. That makes it a little bit more efficient, and the head loss is a little bit smaller, but it is more tedious to clean. And I think we will look into the cleaning process of both filters also next week when we are discussing the operation of RAS. And the downflow filter basically, as I already said, does the same. It's a little bit easier to clean because we just have to suck out the sludge that will build up at the top of the filter from time to time to prevent the filter from clogging. Here we can also calculate the filter size, and usually the recommended flow velocity of rapid flow sand filters is about 0.14 to 0.42 centimeters per second as a flow velocity, and then again based on the total flow rate that we have. And in the sand filter, we usually recombine the flow of the skimmer from the fish tank and the radial upflow filter. So we will again have the complete flow that goes into the fish tank that goes through the sand filter. And then from these two values, desired flow velocity and total flow rate through the fish tank, we can again calculate the needed cross-sectional area of our sand filter. Next step, as I said, will be the biological filtration. And for the biological filtration, it's very important that we already got out most of the solids, because otherwise the bacteria in the biological filter will have to deal also with the solids, which will make the processes in the biological filter much less efficient and also add a lot to the oxygen need of the biological filter. And that's one of the main aspects that we have to take care of in the biological filter. Usually, we need to provide enough oxygen for the bacteria to do their work, to oxidize ammonia and nitrate to nitrate. And we have to provide enough surface for the bacteria where they can live on, so that we have enough bacteria in our biological filter to filter out all the, to transform all the ammonia into nitrate finally. There are many different forms again of biological filters. One very current filter is a moving bed biofilm reactor. It has very good nitrification, also good degassing characteristics, but more or less no filtration. Then we have trickling filters where the water trickles down from spray nozzles above the filter through a huge surface body of plastics that are fixed. This also has very good nitrification, very good degazing, and no filtration characteristics. Oxygen is in this filter here provided by the space, that the empty space where air can circulate inside of the filter, because water only trickles down. There's plenty of air and only a little bit of water in the filter. And compared to the moving bed biofilm reactor, that is quite a different concept, because in the moving bed biofilm reactor, we have really a container filled with water, with some media where the bacteria can live on, and all this is heavily mixed by aerating actively the water body. So we, in moving biofilm reactors, we need an aerator and some means to provide air to this aerator to mix and aerate the water, while in the trickling filter, the air is part of the filter design. And then we have fixed bed filters that can also be just devices that are meant as a filter. But I put here as an example for a fixed bed filter a media bed that may exist in an aquaponic system, because this is basically a biological filter in form of a fixed bed filter where the bacteria live on the gravel that is inside of the grow bed. And the background of this kind of filtration is that it has basically no degassing or very bad degassing, but it can also filter fine organic particles out of the system. So this is also a little bit a dual use, but the main use would be to serve as a biofilter and make at the same time plants grow, obviously, inside of our system. So let's shortly have a closer look at the moving bed bioreactor. As I already said, we will need heavy aeration here that helps us to move the media where the bacteria live on inside of the filter to provide good mixing, but also to provide some movement and scratching on the media so that the biofilm gets a little bit abrasion so that it doesn't get too big and the efficiency of the biofilter remains intact. Oftentimes the classic biocarrier are like the ones we see here. It might be called as K1. There are also different ones. The big advantage of these biocarriers is that they really have a huge surface per volume of the carrier. So 1 cubic meter of coldness K1, for example, provides 500 meters square of living space for our bacteria. But we can also substitute this classical biocarriers that we have to buy with something that we might find locally. And one alternative might be plastic biocarriers like bottle caps that have also quite a high surface compared to the volume they offer, but they are made of plastic. And I think, I don't know in which webinar we already had the question if we are not afraid of microplastics in our systems. And I think that plastic bottle caps probably create this problem even faster than the professional biocarriers. And that's why I also want to mention alternative natural biocarriers, where we see in literature that they are almost as good in the filter capacity than the plastic biocarriers. And two very good examples are coconut shells that we would also cut into like a round shaped pellets, or bamboo that we would probably cut into rings, that both have very good characteristics too with respect to biological activity of the filter. Here also we can calculate the filter size that is needed. If you look at the typical production rate of ton that we have daily in our system in grams per day, and then at the removal rate that is usually given in grams per day per meter square of growing area for the bacteria, then we can calculate how much media we need if we take into account the square meter per cubic meter ratio of the biocarrier that we are using. And then the volume of our bioreactor would be twice the amount of media that we need approximately. And the aeration that we would need would be 5 times the volume of the bioreactor per hour. So we need quite a lot of air. Then, as I already said, in smaller systems, we will probably get away with aeration of our system. Aeration has an advantage that at the same time as we add oxygen to our system, we also get rid of dissolved carbon dioxide, of nitrogen, and of argon, for example. So we have at the same time a degassing function of our aerators and don't only add oxygen. The devices that are available for aeration are mainly diffusers, where we pump air with an air compressor to the diffusers, and they produce coarser or smaller bubbles inside of our water body to aerate our process water. And usually this is done inside of the culture unit. Yes, also either if we need the air inside of our biofilter, we will put the aerator inside of the biofilter, and the same goes for the fish tank. We need air or oxygen for our fishes, so we would put the diffuser inside of the fish tank, obviously. And then there are some methods of adding air to the, or exchanging gases within the water with surface disturbance. Mechanical mixing is one of the methods that is oftentimes used, which also takes place inside of the culture unit. Then we have stair-type drops, where the water drops into our culture unit, and by this means also disturbs the water surface and mixes well, and also gets into contact with a lot of air while it drops down into the pool. And some kind of a combined unit, as I call it, that's an airlift pump that helps us to lift the water level in our system. So it's with low head systems, this might be the only way that we lift the water to gain head in our system. And as we use diffusers inside of the airlift pump to get the water lifted up, we will at the same time aerate the water with a diffuser, and also with a splashing inside of the culture unit. We will also aerate our fish tank while we transport the water inside. So these airlift pumps have kind of a dual benefit, as they gain head and aerate the system. If we are having a more intensive system, we can no longer go only with aeration because the fish would use up too much oxygen. Then we need to supersaturate our process water, with oxygen before we lead it into the culture unit. And the background of oxygenation is that it does not degas as aeration does the process water. So we might run into problems with supersaturation of gases that can produce bubble diseases in our fish. And that's why we always have to have a degassing unit before supersaturating the process water with oxygen, so that we don't have a total gas pressure that gets too high for the fishes. And here again, we have a couple of devices that are usually used for that. One is again a bubble absorption unit. Normally we use, when we oxygenate the water, units that produce much smaller bubbles, also called nanobubbles, because we want normally that as much of the gas dissolves into the water as possible. Best would be 100% of the gas that gets dissolved, because oxygen is expensive. And if some of the oxygen bubbles get out of the water on top of the water surface, we will in fact lose money because we put in more oxygen than was absorbed by the water. And that's the main reason why these systems are usually only used as emergency backups. If other systems fail, that we can still add oxygen to our fish tank, but not as the normal way to provide oxygen to our process water. The two next examples are so-called gravity-driven units. So the U-tube is a device where water is let down about 10 to 30 meters down the earth and then comes up again. And these 30 meters of depth add so much pressure to the water that the oxygen that is let in at the top of the U-type, and that is going down with the water stream to this depth of 30 meters, usually dissolves to almost 100% inside of the process water body, which is very efficient. And as the water comes up again to almost the same height as before, the whole device, even though it goes 30 meters deep, has a very small head loss. And it is technically really quite an easy device. And that's why I like this very much, because you only have to drill a deep hole. That is something you have to manage somehow. But after that, the investment costs and the operating costs and everything are quite low, with a really, really good efficiency. Also, technically quite simple is the so-called low head oxygenators, where we produce some kind of rain or droplets of our process water that run through a chamber that is filled with oxygen, and with a high contact surface that we have here between the drops and the oxygen that is in the chamber, we also have quite a good transfer rate of oxygen to the water. And the advantage is that all the oxygen that is not used up by the water, we can recycle it inside of our system, so that we don't lose much oxygen with this method either. But it only has a medium transfer efficiency, and it's a little bit more complicated probably as a device than the U-tube. And then we have pressurized units that produce a pressurized chamber with a pump overpressure that produces the pressure inside of the device. That is quite energy heavy, so we use the pump energy to produce this constant pressure inside of a chamber. That's why they have quite a high head loss, these devices, but they also have a high efficiency. And it's technically a little bit more complicated than the other devices, also because not the whole water flow runs through this pressurized units, but only part of the total flow, so that we need a second bypass, and we have to take care that the right amounts of water run through the pressurized unit and also through the bypass. So it's quite efficient, but it's energy, it needs a lot of energy and has a high head loss. So this would be the backdraws of this method. That's why I personally prefer the gravity-driven units that are more efficient energy-wise. So last thing that was in our list of devices is disinfection, and this also is really only needed if we have very high fish densities, because with lower fish densities we don't have that much problems with hygiene regarding viruses and bacteria. And two methods are mainly used for disinfection in recirculating aquaculture systems. One is high-intensity UV light, where we just put some strong UV lamps inside of our water flow, and we have to take care that the amount of radiation that comes from the light is big enough and the flow rate is slow enough so that the water gets enough in contact with radiation so that we can eliminate all harmful organisms. It is relatively cheap, and the effect is limited to the reactor. That has its advantages, but also its disadvantages. The largest advantage is that it doesn't affect the fish, and also not the bacteria in our biological filters or whatever. Backdraw is that we need really good solid removal, because if we have still some really small solids inside of our water, this adds to the turbidity of the water, and then light does work less well. That's obvious. And the two other ways are oxidation of the organic substances. That's very common in intensive aquaculture, to use ozone. That's very effective. It's a little bit difficult to dose to the right amount, because if we have too much ozone inside of our system, it goes with the flow and can then enter the rearing unit, the fish tank, and also the biofilter. And if we have too high concentrations of ozone in our process water, this may harm fishes and biofilter. And it's relatively expensive to have this ozone generator inside of the system. And then the last would be H2O2, which is also very effective, but quite difficult to dose. And if we overdose it, we can really severely damage the fish. And that's why oftentimes it's not used on a regular basis for disinfection while the system is running, but more for cleaning containers of the aquaculture if they are emptied and cleaned, or also to treat locally fish that have some problems, but quite carefully in these cases. Yeah, this finally concludes my ride through recirculating aquaculture systems. And at this point, I would like to invite Professor Oyebola to add some of his insights on catfish farming in the Ibadan Living Lab. Over to you, Prof.
Thank you very much, Michael. That was a really inspiring presentation. I've learned a lot even from this presentation, and that's great. My presentation, so we can be able to coordinate well. I want to talk about our experience in the University of Ibadan, what we have been doing, and how we have come to the aspect of the use of RAS and the current situation with the use of RAS. Why are we working on the catfish aquaculture? Because our main focus is the catfish. And what has catfish done for us? We know that fish farming is a global activity and is one of the most important aspect of farming. Farming of fish has become one of the most important businesses that is gradually increasing daily. Nigeria is a fish producer, and the species that we produce mostly is this catfish, African catfish, Claras garipidius. And this production has led to Nigeria being the best producer or the highest producer of African catfish globally, according to FAO 2021. Nigeria is also the second best aquaculture producer in Africa, courtesy the production of African catfish. So our experience have been more in the aspect of aquaculture of catfish. Biologically, catfishes are ray fin fishes. They look like cats, and so they are called cats. And then we can see the biology of the species. I have a number of information here. There are a number of species of catfishes all over the world. For instance, we have the armor catfish, the Silurus asotus. We have channel catfish, Ictalurus punctatus. We have striped catfish, Pangasiadon sanodons. And then we have the African catfish, Glarius garipidius. The picture and at the right side is like a harvest of catfish that we just had from our aquaponics system that is in our system. Yeah. Next slide, please. Yeah. In design for this slide back, Mike. A step back, please. No, before this, there's a slide before this. Okay, thank you. So what are the specialities? Because in designing a system for catfish aquaculture, we need to understand what specialties so that we can be able to capture its effective design. It's only omnivorous species that will take 35 to 45% crude protein diet. And so it means that an implication for nitrogen content in the system. The temperature between 25 and 30 degrees Celsius, so we have to be careful on what to do to not so that when Mike was presenting, he's talking about tolerance level and a situation at which the species will be at optimum. But if you see the ranges, you will understand that the species actually tolerates a wide range of environmental parameters. The pH between 6.5 to 9.0, the optimum at about 7 will be fine. The dissolved oxygen between 3 to 5 milligrams per liter would be at least fine for the species. Nitrite is a very
I think we lost him.
Yes. So what are we going to do?
We wait if he comes back, but otherwise, somebody has any questions that we would that you would like to discuss with us. There was one question that I quite like about the how to calculate the stuff and what do we have to calculate when we are planning the systems. I already answered in the chat and I said, like, yeah, as much as possible, because more you calculate, better it is. But maybe Michael can give some further input on that.
I've already added some comments in the chat. And as I wrote, it's important that we look into every waste product that is produced by the fish and also the oxygen demand of the fish, and that we calculate the needed flow rate for every single substance and compare the resulting flow rates that we need, because it's not always the same substance that decides which flow rate would be needed, because it also depends on the efficiency of the treatment devices outside of the rearing unit. So we really should calculate needed flow rates for every substance, compare, and the largest flow rate resulting would be the design flow rate the system would have to be designed with. And we will do an example for this calculations in the next webinar in 2 weeks on operation of RAS. Then I will go again a little bit more into detail regarding this mass balance stuff and calculation of flow rates.
Any other questions?
Okay.
He's back online.
Thank you very much. I'm very sorry. The network just kicked me out. Okay, so talking about all this comes together to contribute to how we design the system for catfish production, what kind of feeding and how frequent we want to feed, and what is the stability of the feed. All this comes together to give an impression of what to put in place in designing aquaculture system for catfish. In what way are we going to remove the waste that will be coming up from the use of these high protein feed diets? And this aquaculture system is also an issue to consider. What kind of system we want to utilize? Mike was talking about the different system of aquaculture, whether we want to go on extensive, semi-intensive, or intensive system. And this also has to do with the kind of holding facilities that we want to use. Do we want to use heating pond based on the cost, or do we want to use household pond system? We also have concrete system, and we have tarpaulin system. We have floating cages that we can use in lakes and water bodies that are larger to do aquaculture. We also need to think about water control system. Do we want to operate a stagnant renewal system? Is it a flow-through system? Or then are we going to aquaponics system, or are we going to combine plants to help us in the purification in some ways? So we have a number of options that could be based on our level of intensification, or based on the cost of putting these things together, and also based on the economic, the scale at which the farmer wants to operate. Next slide, Mike. Now, before we practice our RAS system, we have some systems that we use. Basically, most of these systems work on inflow of water, outflow of water, oxygen, dissolved oxygen, and getting out the waste. Now, from the first slide, this is a kind of concrete, reinforced concrete system that use water inflow and water outflow. It can either operate on flow-through system or stagnant renewal system. This is an indoor system, and we also have the outdoor system that we use in such a way that we are able to produce the fish under this situation with low cost and simplified system. But it's not the optimum, because some of these things at times you run into some problems. Then we have the fiber tank system, in which you have a circular fiber tank. Michael also mentioned about a circular system, the efficiency of circular system. And we use this in the hatchery, especially for the production of the fry, needing high level of water circulation and oxygen mixing. There are also rectangular tanks that are used. Basically, all of them have inflow and outflow, and then there could be modification on the type of inflow outflow that is being used based on some of these, based on some of the concerns that was actually raised during Michael's presentation. Michael, next slide, please. We also use, we have acres of land where we have concrete, earthen ponds. We have a earthen-based system, and we also utilize a kind of concrete earthen modifications. There are a number of modifications we use because, for instance, the one that has earthen base, we want to try to see that we're moving away from complete earthen pond system. We can still utilize the advantage of earthen-based system to augment a system so that at the end of the day, the farmer is not spending much money in producing an inert-based system. We still enjoy the buffer of the soil-based facility. And so there is earthen-based, and then we have concrete-based system that can be used in that regard. All of these things works on different modifications of water inlet and outlet facility in order to ensure that the water quality is maintained. Sometimes some of these things use a kind of water drawdown system and then an impoundment or a gain to ensure that the water comes up and the fish continue. The water level is also, the level of water also depends on the stage of life. For instance, you keep in broodstock, you don't need high level of water because you don't want to reserve the energy and you want to move the movement not to be too much. If you're raising fingerlings, you don't need so much height because the fish should be using, utilizing energy in swimming, and then you kind of dissipating much energy in movement. So that depending on what you want to achieve, there are modifications to some of these traditional systems of rearing the fish. Next slide. Then we come to the RAS, Recirculating Aquaculture System. This is a typical example of the RAS system, where you have a fish tank, you feed either automated or manually, and then the waste the solid waste is removed, and then in a circular system, the water is purified and it comes back again. What are the benefits? It is water use efficient, and it's very climate smart now because the world is talking about climate, where you are not utilizing effectively the little water that you have. It accommodates for multi-species integration with different systems. For instance, now we are integrating it with plant production in aquaponics. So it has opportunity for integration. It has the ease of operation. The farmer is not running here and there. The system is more stable, and just like Michael had been talking about, you have a system that has a number of precautions that could make the fish to be of optimal condition in production. It's easily quantifiable, and then you can predict, because now you have a system that is not based on nature, but you can actually modify a system to ensure that we have it. Then now that we are having urban challenge and we need to provide food everywhere, it uses less surface area because now everything is compressed. You can stock an high density, and then you can have high yield per square meter or volume of water. There is a control of environmental parameters for optimal production because now the parameters are under control. There is high level of stocking. Some people believe that under aquaponics system, you can stock up to 40 kilograms per meter square of fish. Good water quality is maintained, and this assists in optimum production of the fish. There is protection of the system against weather and predators. Michael was talking about covering and some other things. There is quality control and there is possibility of all year round production. There is higher fish survival and higher yield, and it is less stressful. You can imagine when you want to harvest fish in an earthen pond, the kind of energy you put into it, and in the recirculatory system, you can easily be able to get your fish out within a short time. Next slide, Michael. So, what do we have now? Our aquaponic units have, like Michael was, we have a kind of a use case there, where we have the different units as mentioned by
I think we lost him again, but since we are over time.
Yes. Yeah.
Does somebody still have some questions?
Your own system. We try to use enough of facilities that we can be able to have within our locality. And then you can also have this, the one that works with your system. So we also have a sump where the water flows there and then it kind of redistributes. And the sump is powered by a pump, a low energy consumption pump, because one of the major challenge to recirculatory aquaculture system in Africa is the use of energy and the stability of the energy. And then that's why you can use low cost systems that supply energy like the inverter system. And then you can actually use a low energy consumption pump. So that's it. Next slide, please. Michael. So we also have what you call the water flow into the fish tanks. And then we have the different grow beds for aquaponic system, because we are not just using recirculatory aquaculture system. We are modifying it to include aquaponic system. More interestingly, we are trying to see the performance of this under organic system in which we are not trying to use chemicals. Well, it's a trial, and we could see how it is working, but it's working already. So we have the NFT, we have vegetable, we have the grow bed, and we have series of pipe and a number of things that are joined together to ensure that the flow system works. The issue is water that is nutrient-based will flow into the grow bed, and the plants having phytoremediation power will take off some of the nutrients from the fish and then purify the water, and the water gets back to the sump. And this can, in a way, also assist the system in running, and it's more of nutrients use efficient. We have the NFT, the deep water system, the gravel bed, all of this you have seen. Some of this you've seen when Michael was presenting, and then you can see how people are admiring this technology. The next slide, Michael. So also, we have a kind of covering the screen house, apart from the specific one that we have to screen some pests away in this system, so that at least we have a better covering for our system. Claras garapinos enjoy darkness. And so whatever system we are bringing, we must create darkness. And then darkness is very important. So we need to shade the area where we have our fish, so that then the darkness will be created. Too much light also makes algal growth to be a problem. And so when we kind of screen with dark substances, it also, in a way, reduces the algal growth there. So in order to actually make room for the plant also, we have divided area where we have the plant area that's having light because they enjoy light. And then we have the catfish area that has the dark end. And then the plants are also supported with the number of stakes in the screen house. Next slide, Michael. So, well, in conclusion, the recirculating aquaculture system is a good one because it's reducing the number of stress that is associated with fish production. And it's in a kind of scenario that can be adopted in nearly any kind of environment, and it promises to bring a better return in aquaculture. So we believe with this system, we will be spending less and we'll be having more fish produced. Thank you very much for listening. Over to you, Michael.
Yes, okay. Thank you very much, Prof, for this valuable insights. We are already a little bit over time, so probably let's just switch quickly to our homework for this week to conclude this webinar. This week, we would want you to make a drawing of your existing RAS that you probably already are running at your facilities, or invent some potential recirculating aquaculture system that you would like to build one day. It can be a very simple drawing like you're seeing here on the image with just components your RAS should consist of and some water flows that you would draw in, shortly explain why you included different devices and what they are used for, and then make some copy of the documents that you produced as photographs, scans, or Word, whatever you want, and send it again to my email address to have your homework filed. Yes, this being said, I am done so far with my presentation. I thank you very much for your extended presence this time. And yes, probably Zala wants to conclude the webinar.
Thank you very much. So hopefully you learned something. There was quite a bit more technical that we were used to till now, but I think that all these calculations are really important, especially if you want to design your own systems. So with this, thank you very much, and then see you in 14 days. Where we will discuss the operation of RAS. So we will go step by step, what we learned today and how to actually do the maintenance and how to operate each component. So thank you very much, and then see you in 14 days. Bye-bye.
Thank you.
Bye, see you.
Bye, thank you.
Bye-bye.